Hello and welcome back. Today we're going to be talking about inclined planes. So what is an inclined plane? Well, an inclined plane is just exactly what it sounds like. It's a plane at an incline. It's a ramp, some would say. And in terms of Physics 1 and problems you would be seeing, you need to worry about objects going up or down the ramp. And that seems pretty simple, right? Just going up and down, right? It's just gravity or some guy pushing a box up a hill. Well, maybe it's not as simple as you think, because we need to use trigonometry to actually find anything we want, such as the acceleration of the box per se. So let's do just that. Let's do some trig really quick. Now this is a very, very general inclined plane. Let's say that the incline itself is theta and that this mass m block has forces put on it. Now think about Newton's second law and try and figure out what forces are being acted upon this box. And consider no friction. Well, if you said that there's a gravity force, you'd be correct. So let's make a little gravity arrow here. But that's not the only force. We actually have a normal force. And if you remember from our normal force video, it is always perpendicular to the surface, which means normal force is not going to point straight up and just counteract force of gravity. It's actually going to point a little to the left. Now, just for giggles, let's say there was a force of friction. Which way would it point? Well, given that this box is going to go down the ramp, force of friction would point this way. Of course, it's actually in connection with the box and the floor, but you wouldn't be able to see the arrow if I put it right here. So you may notice something. The force of gravity is skewed from the rest of the forces. We have force normal and force friction clearly making a right angle with each other, and force of gravity being the odd one out. Let's move the FG vector a little bit to the left. Great. So I just extended and put the FG vector a little bit to the left. I made it larger so that what I'm about to do can be seen a little easier. Now, like I said, the force of gravity is the odd one out here between all of the forces acting on the mass. And that's because it's at a weird angle, right? So let's do something funny and rotate our axes. Normally, you'd think up is y and right is x. And you'd be right, that is currently what our system is like. But I think if you stay with me, you'll see that it's easier if we actually rotate these axes. So first things first, what are our new axes? Well, I'm going to recommend having y point this way. And honestly, for x, it can go either this way or that way. To make it clearer what I'm doing here, I'll make it this way. Now, why did I do that? I did that so that it would match the directions of Fn and Ff. You can tell, because Fn is perpendicular to the surface and Ff is parallel, that there's a right angle between these two, which makes it perfect for setting up a new axis. But now we have created a problem. Originally, FG was perfectly easy. It was just down in the y direction, and Fn and Ff were the problems. Now it's the opposite. Fn is just up in the y direction, Ff is just positive in the x direction, but Fg is the odd one out. It doesn't really fit. But it does, and it does because we're working with a triangle, and triangles are really silly. And we can do some geometry to figure out an x and y component of FG. So let's do that. If you rotate your head a little bit, you can see FG from the axis of y and x. And you'll see that the y component is going to look something like this. And the x component is going to look something like this. Now, this is not a trigonometry video, so I'm not going to show you the in-depth way I'm solving this, but just trust me when I say that this angle right here is also theta. It has to do with some trig identities, geometry identities. If you really want to, you can do this in your free time. But that angle being a part of our FG triangle makes it extremely easy to find the x and y components of FG, because we can treat FG as just a scalar value in this case, which means FG would be the hypotenuse of this triangle, because this is a right angle. So that means FG cosine theta is the y component, and FG sine theta is the x component. So, just looking at this, you can tell that FG sine theta is actually the component of FG that is pulling this mass down the ramp. Alright, now that we've done this kind of introductory look into an inclined plane system, let's do a quick practice problem. This problem asks us to find the acceleration of the mass without considering friction, and the only value that we're given is theta as 40 degrees, theta being the incline of the plane. Well, with any system that we don't really know where to start, we should do an FBD. And the FBD that we should do is of the block M. So what's working on block M? Similar to what we were talking about earlier, we have an FG and an FN going this way. Now, once again, to make things easier, we're gonna tilt our axes. So we start at Y, X, and we transition our axes to look like Y and X. Hopefully that makes sense. It's basically to align our axes with the other forces that aren't force of gravity, because force of gravity, we can set up a triangle that's very easy to analyze. So let's do just that. If we go back to our FBD, we can move this. We can make that triangle once again using our new axes to find FG, the y component, and FG, the x component. So FGY will look something like that, and FGX will look something like that. And theta is up here based on trigonometry. So we can say that FGY is once again FG cosine theta, and FGX is FG sine theta. Now, we have to do a little bit of intuitive thinking here, because this is sort of hard to understand. Fn is actually equal to Fg cosine theta. Now, why am I saying that? And how do I know? I'm saying that because of this new axis that we've defined. If we look at a ramp, and we assume its general function is that the mass is going to fall down the ramp, you'd say to yourself, it's moving left and down, right? So in our original axis, it would be moving in the y direction and in the x direction. However, in this new set of axes, it only moves in the x direction, because the x direction is this axis right here. It goes along the surface of the ramp, and the y-axis is perpendicular. And looking at the system, nothing is shooting this mass out into space. The mass is going to stay on the ramp. So if that's the case, that means that there should be no acceleration in the y direction of our new axis. And if we look at our FPD, there are two forces in the y direction, Fn and Fg cosine theta. In order for there not to be any acceleration in the y direction, Fnet y must be equal to 0, which means that Fn minus Fg cosine theta must be equal to 0, which means Fn equals Fg cosine theta. Basically, all this is saying is that the box is going to stay on the surface of the ramp. It's not going to start tunneling down into the surface or flying off into space like Superman. However, there is a net force in the x direction, Fg sine theta. And that should make perfect sense, because the x-axis now is along the surface, and if we let this system go, then the box is going to start dragging down, which means there's some force that must be pushing this mass down the ramp, down the x-axis. And we find that in our FPD to be Fg sine theta. It's going down the x-axis. So we know Fnet x equals Fg sine theta. We also know that Fnet x is equal to max, and Fg is equal to mg, and we know sine of theta is actually sine of 40, because that's given in the problem. And you'll notice we weren't given mass, but we don't actually need it. Our masses cancel out, which means a of x is equal to g sine 40 degrees. And if you look at our original problem, we're asked to find the acceleration of the mass. So we know g, we know sine of 40, and we could take out our calculator and do 9.81 meters per second squared times sine of 40 to be, you could take out your handy dandy calculator. And so g times sine of theta turns out to be 6.31 meters per second squared. And that's our ax value, which in this case is the only a. There is no ay in our new axis because it's not going that way, it's not going this way. And so we have solved the problem. We found the acceleration of the mass. Pretty cool. Now I'm going to add another little tidbit into the problem and make it harder. I know, you can't wait to find out how I made it harder. Well, I made it harder by introducing friction into the problem. So if we go back and do an FPD once more, we have Fg, we have Fn, but we now have force friction. I'm adding a whole new force into this problem. Now, first off, this FPD does look familiar, minus the FF, and I'm going to go ahead and steal what we did here. Let's copy this. So I'm going to go ahead and tilt those axes once again. You just have to trust me that doing the trig with one force is easier than two force. Let's say if we did keep the normal xy plane, we'd have to figure out x and y components for both Fn and Ff. So that's double the amount of work if we just tilt the axis and we only have to do trig for one function. And it's also just much easier with Fg when it comes to triangles. Now, the analysis of this problem is actually really similar to the first example. I know I said I'd make it harder, but I'll be honest, it's really not that much harder if you really think about it. We're going to do the exact same analysis we did before, where we have Fgy and Fgx. Fgx equals Fg sine theta. Sorry, I forgot to draw theta here. It's over here. And Fgy is equal to Fg cosine theta. With the same reasoning as before, I can say that Fn is equal to Fgy, which is Fg cosine theta. I can say that because once again, our box M is not flying off into space or tunneling into the triangle, so it's not moving in the y direction. In order to not move in the y direction, there needs to be no acceleration in the y direction, which means f net equals 0. It's exactly the same thing as we did in the last example. Now, f net x is actually a little bit different. F net x is equal to, I put x positive going up, so it'll be ff minus fgx. And we can go ahead and make some substitutions here. First of all, f net x, according to Newton's second law, F equals ma, so F net equals max. Ff, if you remember the formula for the force of friction, it's equal to Fn mu. Mu is the coefficient of friction, Fn is Fn, and we were given mu at the problem. Mu for kinetic friction is 0.4 between the block and the ramp. So Ff is equal to Fn mu. Now Fn is also a value we know. I just wrote it down right here. It's Fg cosine theta. So Fg can also be substituted into mg. I just said a lot, so I'm going to write down all those steps that I just did. Ff is equal to Fn mu. Fn from this step is equal to Fg cosine theta, which is equal to mg cosine theta. So then we could say Ff is equal to mg cosine theta mu. Hopefully you followed all that, and we can replace Ff with mg cosine theta mu. Now fgx is quite simple. It's fg sine theta, and fg sine theta is equal to mg sine theta. So we can do mg sine theta. And once again, you'll notice we have m's in every term, which means cancel, cancel, cancel. Isn't that beautiful? And we're left with ax equals g cosine theta mu minus g sine theta. We can clean this up to get g cosine theta mu minus sine theta. And we can go ahead and plug in some numbers. G, 9.81. Cosine, our theta is 40 degrees. Mu is 0.4 minus sine of sine of 40 degrees, sorry. And you can take out your handy dandy calculator, which I'm about to do. 0.4 times cosine 40 minus sine 40, all times 9.81. And you can calculate that AX is equal to negative 3.299 meters per second squared. Now, why did I get a negative value? Well, it's because I put positive x pointing up the ramp. And by logic, you know that if you were to let this system go, the box would move down the ramp. So it should make sense that AX, or A of the surface along the ramp, would have a negative value because it's going in the negative direction. Which leads me to a small correction I have to make on the first problem. In order for this answer to be correct, I would have to make the x-axis positive in the other direction. That is my fault. I didn't catch that the first time. Alright, that was a quick introduction to inclined plane problems. I hope you enjoyed and learned something, and thank you for watching. See you next time.